I am today. I am planning to discuss a little bit about flow dynamics. Basically, that is called shear flow. Okay, and then we will discuss analytical aspects of this flow dynamics by using structural bifurcation analysis. So my topic of today's lecture is unsteady flow separation in laminar shear flow past Bluff bodies, a structural bifurcation analysis. So basically, from the title, you can see that two aspects. One is shear flow. So I will discuss what is the shear flow a little bit on that. I hope you are from a chemical background, so you have the idea about shear flow, right? And along with that, the structural bifurcation analysis, the new aspects or new tool for exactly finding out the position and time of occurrence of circulation zones. So I will discuss on that. So I am Dr. Rajendra K from the School of Basic Sciences, IIT Mandi, Himachal Pradesh. And this work is basically the PhD work of my student Rajendra Kumar and some of those last few parts of my other students, Osini and Amarjit. So starting with the laminar shear flow. So basically, you know that shear flow is the flow. Just a minute. So shear flow basically is one of the important aspects of fluid dynamics. So basically, shear flow means, if we say in one word, that is basically boundary layer flow. Means when you have enough viscosity, and that means your the full domain is of kind of boundary layer. Okay, so in reality, when the wind flow behind these high altitude buildings, or through this this breeze, or let's say in ocean, if there is a ocean source from where you have pipelines, so all these type of things experience these shear flow effects, and due to that, this has an impact on real life situation. So study of the vortex shading or study of the behavior of the fluid flow is an important aspect. So this type of shear flow can be discussed in different ways. So basically, flow separation means when, let's say, for a boundary layer, when the boundary layer travels for a long enough distance, then there may generate some adverse pressure gradient, and if there is an adverse pressure gradient, then it is we basically become detached from the surface of the cylinder, surface of the body, and due to that detachment, some backflow occurs, and due to that, gradually the flow separation or circulation zone develops. So this is basic property of fluid dynamics, and it's passing through some solid surfaces. Okay, so now this type of flow study can be done in different ways. One of the important aspect is, let's say, you can do it through experimental point of view, but you know that experimental setup is one of the very difficult task, because your large scale problem, you have to make it in a very small scale environment, and then also many times this fluid separation or the property changes very rapidly, so it is very difficult to capture using experimental setup. So another aspect is, you can, if you have the governing equation, you can go for the analytical solutions, because analytical solution gives you exact result. But still, for most of this type of complex fluid flow, because the governing equation is basically Navier-Stokes equation, and it is very difficult to get an analytical solution for that. Only few very simplified case has analytical solutions. So those two aspects, though they are very important, but it is very difficult to use them. So the next direction is to use numerical methods, and due to the rapid development in programming environment or computer efficiency, now these numerical methods are nowadays very useful tool for studying all the complex fluid flow problems. So there are different numerical approaches. One of them, and oldest also, and very simple frame of settings, is finite difference method. So finite difference method is basically has developed let's say in the beginning of the last century, around 1930, around that time, means numerical methods used for this fluid flow problems. But after that, when the development of high-speed computers, these numerical methods got popularity, and now you can see that lots of things are happening through numerical techniques. So finite difference method during 80s, second order accuracy was enough, because at the time the computer was not so fast, and we also not interested in getting very accurate result. But due to the development of new high-speed computers, now we can go for any that means any height, means we can go for a higher number of grid points. We can take more complex phenomena. If we have a large set of equations, still we can solve it very easily. So now that's why now only second order accuracy is not going to work. So we need some higher order accurate schemes. But the problem is, if we increase the order of accuracy of different derivatives, so it will basically increase the bandwidth of the coefficient matrix coming from the discretized equations. So when finite difference method used, so basically what it does, it basically discretizes your differential equation to a difference equation, means system of algebraic equations. Okay, and to do that, you have to first discretize your computational domain. Okay, and then that will give you some set of equations, and you have to solve them. So if we increase the order of accuracy, ultimately it will increase the bandwidth, means the number of non-zero elements will be more in the coefficient matrix of the discretized equation. So so that will basically, obviously, it will increase the complexity or that means computational time. Again, if I go for, let's say, if we want to get better accuracy in a very small domain, so we need a refinement of the grids. This will also increase the number of grid points, and obviously it will also increase the time. So our interest is to develop a method which can give higher accuracy. Also, there needs less number of grid points. So one of the very popular and important method is called higher order compact scheme, or it is called HOC scheme. So this scheme, you can see it is higher order accurate as well as compact. So a scheme is called higher order when the accuracy is more than 2. So any numerical method which has accuracy more than 2 is called the higher order accurate. And compactness means when we are discretizing, for around which we only take the exactly directly adjacent points. So for example, if I discretize around ij point, so I only need these 9 points to discretize my governing equation. So this higher order compact scheme has both the advantages. So for our case, usually in fluid dynamics, you can see that most of the changes happens in the space, means space direction. In time direction, you don't need that much that means accuracy. So for our case, we use HOC's accuracy in space direction, means xy that means direction in 2-dimensional case, or xyz in 3-dimensional case, and we take only second order accuracy in time aspects. So to get this type of higher order accurate scheme, there are different mechanisms. One of them is by using original PDE. So basically, when we use finite difference scheme, basically we are basically using Taylor-Swift expansion to discretize the partial derivative terms, and then we use central difference to get the discretized system of equation. But if I want to get higher order accuracy, so we have to take more number of grid points. We'll discuss that. Okay, so how we are using original PDE to increase the accuracy of the approximation of the derivatives. We'll discuss that. But we will be using original PDE, means by using the governing equation, we can increase the accuracy, so that my tensile will be, it is called the tensile, it will be compact, means only we will be using directly adjacent point. This is called the 9 point tensile. Okay, now this higher order compact scheme, what I am going to use, basically the first it was developed by Lax-Wandruff. It is famous method. If you go through the finite difference scheme, the Lax-Wandruff scheme is one of the very popular method. So it was used to increase the time accuracy in 1960s. After that, in 1988, McKinnon and Carey, and then McKinnon and Johnson in 1991, they used the same idea to increase the spatial accuracy, means accuracy in the XY direction. Okay. After that, in 1995, Post and Carey first used this idea for fluid dynamics, basically steady state stream function vorticity formulation. Okay, and later on in 2000 onwards, Kalita et al. Okay, they developed this scheme in a better way and in scale. Okay, in different aspects. So Kalita in 2002 first developed this idea, okay, this method for steady state convection diffusion equation, and they then developed non-uniform grids, and then in 2008 they developed the higher order complex scheme for unsteady cases. Okay, and in 2009 because Kalita was my guide, during my PhD we developed a more general case that is for the flow pass impulse instability started circular cylinder. Means we now extended this for any generalized case. So this polar coordinate case can be extended for any type of that means coordinate systems, and this is more general form. And now my student Mittal, he has extended this for that means more complex flow, like flow path rotating cylinder, and then we have extended this for immersed interface. Means when you have a jump in between. So let's say you have two different materials and there is a jump, there is a interface, and their interface has a jump. So that also can be tackled easily by using some technique along with the HOC scheme. So we have extended that also. So now HOC method is quite the popular method, and it can be used in any aspect of the fluid dynamics, and it has given excellent result for fluid dynamic problems, solving fluid dynamics problems. Now another aspect is, as I discussed, is called structural bifurcation. So basically structural bifurcation is first, the term bifurcation was used by Henry Poincaré in 1885. The idea is basically if I discuss in terms of fluid dynamics. So let's say if I change a little bit, if I vary a little bit in the parameter, if it change rapidly in the topological aspect, means I am changing little bit of, let's say, change in time or change in velocity. If I can get a huge difference in the flow phenomena or the topological aspects of that, then it is called the bifurcation. So in two-dimensional, viscous fluid flow, past Bluff bodies can that means have number of these bifurcations. So it is an important tool to use bifurcation or topological aspect with bifurcation analysis to discuss the flow separation, because if flow separation is happening, then there will be a bifurcation, and I can get the exact point and also the time of occurrence of the bifurcation. So if I know that, it will be very easy for me, or it will be very useful for application point of view. If I know at what time, at which place it is happening, then I can do many things, or I can handle that particular point in my requirement, so that I can either compress the vortex shading, or I can increase the vortex shading. So many things can be done, and due to that I can have different applications of that. So structural bifurcation in one-dimensional case is the definition is given by Ghia et al. But our interest is to develop or to test the structural bifurcation for our this to get the position and the time of occurrence of this recirculation zone is basically governed by these four equations, either the four equation in equation 1 or equation 2. What is that? So basically, if I take the surface vorticity plot, then the bifurcation occurs when these four relations simultaneously occurs, either this set of four equations or this set of four equations. What are these four equations? Basically, particular that point, my vorticity will be 0, because bifurcation means at that particular point there is no vorticity, or that means the particular point, so vorticity will be 0. Then what is called the tangent would be along the x direction. So that's why the divergence or first derivative in x this space derivative. So this determines it is space x or y, whatever it is. So del y, del omega del x or del omega del y equal to 0. Means tangent will be along to x direction or y direction. Basically, we are considering x direction here. And then second derivative is going to be second derivative is equal to the second derivative equal to 0. Greater than 0 means basically there would be a local minimum. And time, if this is local minima, then I will be having a increasing time, then decreasing time. Or if I have a local maxima, then it will be increasing time. So three relations are on surface vorticity and one equation on time. Okay, so if these four relations, okay, at a particular point P star and particular time T, okay, particular time T is happening simultaneously, then I will say that this point P star and T star is basically the point of bifurcation at time T is equal to T star. Same thing for this. So after okay, computation, we will first check the flow phenomena, and then we will try to check that at which particular point or at which time I can the vorticity satisfies these relations, and then we can say that this is my bifurcation point. We'll discuss. So basically, throughout my this lecture, I'll be using this non-dimensionalized form of stream function vorticity of Navier-Stokes equation. So basically, this is the this vorticity equation, this is the stream function equation, and corresponding uv in terms of the stream function, and omega can be represented by u and v. So basically, these are the common equation. It is very easily available. Now, to use HOC, I'm just giving some hint about how to use the HOC discretization. So basically, this equation is nothing but the Taylor's expansion of a particular variable. So now, usually what we do, we take first two terms to get central difference. But in our case, we will be using up to, let's say, higher derivative, up to fifth order derivative. And then my approximation of first derivative del psi del x would be equal to, this is basically the central difference operator, this part, plus this third order derivative term, to get a fourth order approximation of the first derivative. Correspondingly, to get a fourth order approximation of the second derivative, I need to incorporate the fourth order derivative. But I cannot use direct central difference, because if I use central difference, it will take more than compact tensile. It will take 4 points. It will take 5 points. So what we will do, as I told you, so we know that this is my equation, stream function equation. So if I differentiate this equation with respect to x, I will be getting del q psi del x cube. But in that case, it will be having a tail. So it will be del q psi del x del y square, and this will be del omega del x. So it will be third order, but this term will be second order in y, but first order in x. So this term can be replaced by these two terms. And if I again differentiate it, it will be del 4 psi del x to the power 4, and this will be del 4 psi del x square del y square, and this is second order del omega square del x square. So this fourth order term can be replaced by these two terms. That means I can replace my these two terms in terms of second order differentiation along x and y directions. So all the terms in the right hand side will be either second order or lower order in x and y. So I can use central difference to get the fourth order accuracy. So I will be getting a fourth order accuracy, but with the help of successive differentiation of governing equation, I can get a compact tensile. So the same thing I can go for the y derivative also. So this is a basic idea about how I can use HOC scheme, which we are using. So after discretization, so we can have this type of relation. So here all the coefficients a11, a12, basically they are function of u, v, now the time derivative or the space time, discretized time delta t or delta x, or their derivatives. So basically these equations are though it is looking a bit complicated, but when we are using computer code, then it is very easy to handle. If computer will take care of all these things. So we use the HOC discretization and to solve the system of equation. So basically this will give me a system of equation. So let's say if I take n cross n grid size, so I will be having an n cross n into n in cross n into n matrix, coefficient matrix. So basically I have to solve that many equations. So to solve this system of equation, we basically use advanced iterative solver, that is called hybrid biconjugate gradient stabilized method. So this is a method which can easily solve system of algebraic equations, if it is nonlinear also. So we used HOC along with hybrid biconjugate gradient stabilized method to solve the problem. So we start with the problem shear flow pass single straight square cylinder. So this is the schematic diagram of the problem. So we have initial, so that means inlet we are taking simple linear shear flow. K is the shear parameter value. So depending upon K, it could be simple flow. If K is equal to 0, it is simple flow. If K is a non-zero, it will be a shear. And if we increase the value of K, obviously shear will be increased, more viscous. We have taken, so this is an infinite domain. So for computational purpose, we have taken a okay, computational domain where I have taken okay, an arbitrary upper and lower bounds. So so far, so that it should not, okay, that means should not hamper the flow phenomena. Okay, and in the downstream outlet we have taken convective boundary condition. So convective boundary condition is quite okay. That means quite that means interesting boundary condition. There are so many different boundary conditions available in the literature, but we have seen that convective boundary condition is okay, the best for HOC environment. So and these are the other boundary conditions available here. So now what we have done, so basically for any okay, numerical these computations, you have to first check the grid independence and time domain independence to check that your method is working fine or not. So we have taken different grid sizes to check that the values, okay, for a particular point, okay, the UV, psi, omega values are okay, almost same or not. So we have seen that if I take 801 cross 276, this grid size, it is quite okay to get quite good okay result, which is not influenced okay so much by the grid size. Now to get the time independence, we have taken the grid size of same thing, 801 cross 276, but three different time time level we have considered, and we have seen that if I take 0.01, it is quite good to get okay the good solution. Or that means, so we have used in my the computation, the grid size is 801 cross 276, and del t means the time okay level is 0.01. So before going to discuss our results, first we have validated our result. You can see that this is a comparison of our result with the result of Cheng et al. Of 2007, and you can see that our result is matching very well with their result. So after validation and okay, the independent grid independent time independent test, now we can go for our study. So what we have done, first we have taken that means RE means the Reynolds number is equal to 100, and we have taken different parameter values of different okay, Shear parameter values. So when k is equal to 0, as I told you, this is basically nothing but a simple flow, means simple flow past a cylinder. But when k is non-zero, so 0.1, 0.2, 0.3, 0.4, for this case it is a shear flow, and with the increase of k value, the shear is increased. So if I show the animation, you can see that when k is equal to 0, simple flow, you can see that the vortex is heading exactly in the middle. So that is symmetry is there because there is no shear in between, and that is why the vortex is heading almost of the size of same size from both up and down. Okay, or upper side and downside of the cylinder. But when I have incorporated that means the shear value, you can see that upper this vortex shading, okay, the size is different from the lower, because you know that shear what is called the shear parameter, due to that my velocity is increasing with the increasing in y direction. So when we will increase in y direction, so velocity will be more, and due to that the effect is here. So now if I see for k is equal to 0.3, you can see almost the lower vortex is suppressed. Only the upper vortex is shedding from okay the downstream. So this is basically due to the effect of the is equal to 4. There is no okay no vortex shedding. It is exactly fixed. That means vortex shedding is totally suppressed when we have increased the shear. So without increasing the Reynolds number, if I increase the shear value, I can see that the vortex is suppressed okay due to the shear effect of the flow. So this is for R is equal to 100, and now it is the streak lines. So streak line means actually the same flow, but if you drop some colorful dust, then how this dust will be okay moving, that is basically called the streak lines. So if I see that the movement of the streak lines, you can see how basically flow is occurring. So you can see that the two okay vortexes heading from top and bottom okay side of the cylinder, and basically of same size okay and almost in the same frequency. But with the increase of increase of k value, you can see the vortex heading okay the shape and size is totally changed. And for example, if I take let's say k is equal to 2, 0.2, you can see the vortex shading has a different different shape, or vortex shading has a totally different phenomena, because due to the, as I told, due to the effect of the shear, the down downwards vortex has suppressed in a cylindrical shape, but the upper vortex is setting as it is. And obviously, like k is equal to 0.4, there is no vortex shading, so it is basically there is no periodic nature of the flow. So that can be seen from this phase diagram. Phase diagram basically gives you, if your flow is periodic, then it will give you a closed curve. If it is not periodic, so it will give either that means some line or nothing, because you can see for k is equal to 0.0 to up to 0.3, you can have the closed circles or closed curves, which basically says that they are periodic in nature. But for k is equal to 4, it can have only a point. So that means there is no that means periodic nature of the flow that is confirmed by this. Now, if I use a higher RE value, so the things are almost same, but you can see that the flow pattern has been totally changed. Now the frequency of vortex shading is decreased, means number of vortex shading with particular time is decreased due to the effect of the RE value. And also, if you see the flow pattern, you can see that the flow pattern also has been changed, but the frequency, means the frequency is increased than for R is equal to 100 value. And in this case also, you can see for k is equal to 0.4, the vortex shading is stopped. And this is corresponding to kick line patterns. So the kick line patterns also have a nice behavior. So you can see that the flow pattern for k is equal to 0.2, and you can have a bit more, because you can see that this the what is called this vortex shading is happening in more bigger region than only R is equal to 200. So these things almost same like 100 case. I am just going to the more bigger value of R is equal to 500. This is basically a moderate number. In this case, the flow pattern, or you can say that the flow behavior is totally changed. And you can see that a behavior of the vortex shading is also changed. Something. So vortexes also have a different type of approaches sometimes. So basically, it is, you can see that there is not one or two vortices heading from top and bottom. There are different type or size of vortices are changing setting. That the meaning is that there are frequencies more than one, means there are more than one frequency available for R is equal to 500 and k is equal to, let's say I'm saying 0.2. And the same thing happening for, if I consider 0.3, you can see there are few vortex heading from the bottom line, or some of the things are heading from the top line. So again, you can see that there is a basically two single vortex heading from top and bottom with a different frequency and different size or strength. But one important aspect here is, you can see in that case, for k is equal to 0.4, vorticity is there is a vortex shading. Means for R is equal to 100 and R is equal to 200, for k is equal to 0.4, there was no vortex shading, it was suppressed. But with the increase of RE value, for k is equal to 0.4, we can have a vortex shading. Means here the property or the flow phenomena has totally changed for R is equal to 500 with respect to R is equal to 100 and 100. So we can see all these things. So I am just giving let's say the animation of k is equal to 0.3. So you can see how the flow is the vortex is heading behind the solid surface. So these are basic things. I have not gone in details because there are other studies. I have just left to give you some idea about how this can be checked with the structural bifurcation analysis. So as I told you, structural bifurcation happens only when all the four relations, means W, this surface vorticity should be 0 at that particular point and time. Also the tangent, that means the first derivative should be 0, second derivative should be greater than or less than equal to 0. If it is greater than 0, then it should be less than, and if it is less than 0, it should be greater than. And if I see that at particular point minus 0.22 and x is equal to minus 0.22, and t is equal to y is equal to 0.5, and time, okay, t here is around 1.2, something like that. So if I have this point and this time, we can see that all the 4 conditions are satisfied. You can see that this is a local maxima, and this is a local minima. As I have taken k is equal to 0 here, means it is basically symmetric in nature. So two pair of, okay, it's a one pair of vortices are growing in the same time. So vortex, that is the bifurcation is happening at the same, okay, time, but in just two opposite, because you can see that minus 0.2 to 0.5 and minus 0.2 to minus 0.5. That means you can see that this point and this point, top and bottom side of the square cylinder, but at the same point, same time, because this is due to the symmetry. If I see the zoom view, okay, and if so, as I told you, what is called a bifurcation. So very small change in a parameter value, it has a huge change in the flow phenomena. So you can see that a particular time t is equal to 238 when the bifurcation occurs. Okay, so at that time you can have a very small, okay, vortex or very small, okay, that means vortex is going here. But if you see before that, there is no, that means vortex, that means every the streamlines are, okay, attached with the surface, but after that I can have a bigger vortex. So basically at particular point, the first this bifurcation happens, and after that they can have a circulation. And if I see the behavior of the surface vorticity, you can see when this is happening, this is not touched. It is not touching the x is equal to 0 line. But at particular this point, it has touched, so I can have a degenerate singular, okay, point here, which basically gives us the bifurcation. And at this particular point, you can see you can have a two non-degenerate, okay, non-degenerate points. So that means now I have crossed the x-axis. It's the same thing if I go for the local minima. So when it touched, this is basically this point, and before that not touch, no bifurcation, no singular point, and after that there are more than one singular points. Okay, so basically this is exactly, okay, that means telling us what is happening at particular this point. So these theoretical aspects can give us exact timing, exact, okay, point where this bifurcation is happening. So this is very useful tool to get exact location and time. So this is for k is equal to 1, exactly the same thing, but in this case, as it is a shear flow is there, so it is non-symmetric. So I can get P1 and P2, means P1 is first bifurcation point and P2 is second bifurcation point, two different at different times. And here we have given a table, okay, the first bifurcation and second bifurcation for different RE values with different k. So you can see that there is no such, okay, pattern of getting the time. So it is basically from k is equal to 0 to k is equal to 1, time is decreasing, then it is increasing. Okay, but in that case also there is the same pattern. But once it is R is equal to 200 or 500, you can see that it is decreasing gradually. So from this, okay, up to this, and then it is increasing here. So though there is no such pattern, but you can have some idea that when it is k is increased, the vorticity is, okay, developing more quickly than the lower k values. Now we have taken the next problem, which is basically flow past inclined cylinder. So when I have taken inclined cylinder, the basic, okay, idea is here you can see my corner points are basically the two corner points are in the front and in the back. Okay, and due to that some effects will be arriving. Other boundary conditions are almost same. Here we have shown the validation, so with Un et al, and we can see that our results are matching very well with them. So the study, okay, is okay. Now here it is for R is equal to 0, R is equal to 100, and k is equal to these four values 0, 0.1, 0.2, 0.3, and 0.4. In this case, you can see that though for the straight cylinder, for k is equal to 0.4, it was, okay, the vortex was suppressed, no vortex shading was happening. But in this case, for R is equal to 100 itself, we can have a vortex shading. And if you see the flow behavior, okay, it has a nice, okay, flow pattern, which is quite, okay, nice in shape. And we can see that this is for k is equal to 0. Okay, this is for k is equal to 0, not k is equal to. This is for k is equal to. This is for k is equal to now 0.1. And if I take for this, let's say k is equal to 0.3, so you can see how the flow is, okay, moving. or how the vortex is setting in the downstream. So again, depending on due to the shear parameter value, the symmetry is no more there, and you can see that the vortex heading from the top of the cylinder is a bit more bigger in size and shape, and in the bottom side of the cylinder is a bit small, and it is in cylindrical shape. And if in this case, if we see that you can this from phase diagram, we can see that the for k is equal to 0.4 also I have got a closed curve, means the periodic vorticity is there, and that means vortex heading is happening and it is also periodic in nature. Now for r is equal to 200, you can see the flow is more complex than simple straight cylinder. And if I see if I see, let's say for k is equal to 0.3, you can see the flow pattern is something different. Now it is more complicated in nature. The interaction between upper vortex and lower vortex is is more, and you can have a pattern which is a bit different from the other vortex heading. But in this case also you can have a vortex heading from for k is equal to 0.4. And the same thing we can see from the phase diagram that for k is equal to 0.4 also it is that means vortex is heading as well as it is periodic in nature. So for all the cases the vortex heading is periodic in nature. Now for 500, you can see the complexity, how much the complexity is. Only for k is equal to 0 itself I can have a very complex flow phenomena, and in this case the frequency is also increased. Now you can see that the distance between two is there. And another important aspect, you can see that at a time a pair of vortex is developing, and basically this shaded. So you can see two at a time. So this is a totally different phenomena happening for at r is equal to 500, and you can see it is more effective when you have a k non-zero values. You can see these two vortexes are heading together. Again after some time, again two vortexes are heading together. So basically you can have two consecutive vortices, and then there is a gap. Again two consecutive vortices are heading, and this is basically quite a that means new. I can say that new phenomena we have seen. It has not been reported beforehand. So these things are that means though there are a few papers available for shear flow, but we are first fully studied shear flow of phenomena by using our HOC scheme, and we have got very nice phenomena. And many times you can see that there is somehow turbulence effect is coming here in the downstream due to the effect of the interaction and due to the effect of the high RE values. So we have shown here again the phase diagram. In this case also we have shown the first and second bifurcation points, and as you see for k is equal to 0, symmetry is still there because it is obvious symmetry will be there, and so these bifurcation points can be seen here. So here you can see at the particular point where bifurcation is happening, you have a small vortex developing. Before that there is no vortex, no bifurcation, which means that the streamlines are detached from the surface, but in this case it is not detached, and in this case we can have a big vorticity, and that can be seen from this surface vorticity plot. So it is a in this particular time you can have a local maxima, and before that there was no these singular points, and after that there is a pair of non-degenerate singular points. So the theoretical aspect is satisfied. Here is we have shown all the first and second bifurcation points when it is occurring. In this case, you can see very nice behavior. So if you see, it is basically almost happening in the same time or a very close timing, all the cases, because due to the smoothness of the cylinder that means side in the downstream, the changes is not so much. The time the points, and also if you see the time is gradually decreasing. So from 0.27, 0.23, 0.18, then it is gradually decreasing. So there is a nice pattern of the development of the bifurcation or development of the circulation zone, and this is this is quite different from the straight cylinder case. And if you see, we have shown here by plotting the bifurcation points. So you can see it is basically for the first bifurcation, the time of occurrence is basically gradually decreasing. with the increasing of K values. On the other hand, for second bifurcation, it is gradually increasing with the increasing of K values. So that is totally different, behavior of first and second bifurcations. Now come to the pair of cylinders. Okay, these are basically arranged in a series. So in this case, there will be an interaction between the vorticities, okay, in the downstream. So depending upon the distance, we can see that how the interaction is happening, how the flow behavior is changing in the downstream. Okay, the vortex setting phenomena. So basically, this is the schematic diagram. Again, the things are there. Only the distance is okay. We have taken in terms of the d. If I take this is my d. So how much d? So we have taken. So we have taken basically three different cases. 0.5d means the half of the length. Then 1d means the length, and then 3d. So that we can have aspects of different distances. Again, you have shown the comparison, and you can see that exactly matching. Now come to the behavior. So we have taken s by d means the distance is half of the length of the edge or side of the square cylinder, and r is equal to 100. You can see that basically they are behaving almost like a single cylinder, as they are very close to each other. There is nothing happening in between. So they are basically behaving like almost a single single cylinder, and behavior is almost like what we have seen for a single state cylinder. And we can see that again the thing is that where k is equal to 0.4, there is no vortex setting, and but for 0.0, 0.1, 0.2, we can have a vortex setting, and that can be seen from phase diagram. When r is equal to 100 but distance is 1, there is a little bit of interaction. You can see there is some vortex is developing in between. But as I told you, due to the less space, the interaction is basically the vortex is not growing that much rapidly, or this is not fully developed vortices. Okay, so the effect is coming in the downstream, but you can see some vortex is developing in between. So from the upstream cylinder, a little bit of a small vortex is developing, but due to the effect of the downstream cylinder, it is not getting a chance to grow up. Now when we increase the distance, now we can see that the interaction is very much there, because now this upstream cylinder has enough space to develop its own vortices, and when it is coming to when it interact with the downstream cylinder, there is an interference between these two, and we can have a different type of this flow development. And if you see that for k is equal to 0.3 itself, we can have a different phenomenon. Basically you can see that the lower vortex is developing quite in a lower position than usually it is happening for a single cylinder. And for k is equal to 0.4, though it is no vortex is shedding, but you can see the pattern is totally different. So this is quite nice behavior of the flow, and interaction is there. Now for r is equal to 200, the things are exactly same, and it is behaving like r is equal to 200 for the single cylinder types. But so here we have shown the bifurcation analysis, and again we have checked that. Here you can see that this red color is basically the pressure. Here we have calculated the pressure also to show that where my bifurcation is happening, by default there should be some pressure fall or pressure difference, and it can be seen here. There is pressure difference at this particular 2 points. So the bifurcation where is happening, we have a pressure difference, as well as you can see there is a local maxima and local minima in the surface vorticity, and at the same time my time gradient is decreasing or increasing according to my requirement. So the P1 and P2 are the two bifurcation points. So here for k is equal to 0, they are basically coming at the same time, because the vortices are symmetric in nature for simple flow. But for when k is equal to non-zero, it should not be symmetric. So here we have shown that how the happening. So basically this is for the from the first cylinder, means it is basically from the upstream cylinder we have shown here, and corresponding time table we have shown here. So basically this is P1 and P2. This is basically for the first and second bifurcation from the upstream cylinder, and you can see that here also if we see that there is no such pattern. So basically this is almost same like our single cylinder case, but obviously we can have a different timing of occurrence of the bifurcations. Now the main aspect here is for downstream cylinder. You can see the downstream cylinder for k is equal to 0.2, 0.3 and 0.4, there is no second bifurcation, means only one bifurcation is happening, not in the second. So only one bifurcation can be seen, or one circulation has been developed, but not the second one. If there is any circulation happening, but if it is not satisfying these four relations, we cannot say that is a structural bifurcation. So bifurcation is also of two types. In a usual scenario, one is coming due to the edge, means let's say I am taking a square cylinder, so these four edges can give me a bifurcation, but those bifurcation will not satisfy all the four conditions, so we cannot say those are structural bifurcation. But structural bifurcation is coming due to the interaction of the fluid layer with the surface of the cylinder. If this is the case, then only these four conditions simultaneously satisfies, and we can say that there is a bifurcation happening. So that in these three cases that is not happening, and due to that we cannot have a second bifurcation point. But in k is equal to for s by d is equal to 2, we have only one less, means we have first bifurcation is happening but no second bifurcation, because we have seen that only one vortex is shedding, so that means that vortex is basically developing. And these are the plot of the vortex. You can see that the nature of the vortex is basically red is the 0.5, then 0.1, 0.2 and 0.3. So it is increasing, and also the same is increasing, but the nature you can see that there is zigzagness. But in the second bifurcation you can have a straight increase in time. So with increasing in k values, when your shear value is increasing, then your second bifurcation is taking time to develop. So and this is for the downstream cylinder. Here you can see that the things is totally different. Here it was zigzag in nature, but in this case you can see it is gradually decreasing. Means when k is increased, the vortex the bifurcation time of bifurcation is gradually decreasing. So we need less. That means within a few second, or let's say very after starting of the flow, it separates. On the other hand, it is basically the time is increasing with increasing k values. So these are very nice that means properties we have seen for the first time, because nobody has studied those things of a complex fluid flow. Along with that, we have also studied another mathematical aspect of that is called the saddle points. Saddle points means at the point when you have the flow in different directions. If I take the flow as a velocity profile or direction vector, then at particular point, if I have the direction of all the way, then it is called the saddle point. So you can see that for this point here, S is a saddle point, because I have almost all the direction I can have that means flow directions. And this center means when I have a circulation zone, the center of the circulation is called the center. So C1, C2, C3 are the centers, and S1 is the saddle point. So we have seen that there is this saddle point in the downstream cylinder, and you can see that the saddle point is gradually changing his position with the increase of k values. And if you see for this particular point, you can see the saddle point is happening here, and within this saddle point I have another saddle point. This is totally a new phenomenon we have seen, that a saddle point is a saddle point S2 is within a saddle point S1. That is basically a new thing we have seen that has not been reported also before. So a saddle point is there within a saddle point. So that is a quite interesting phenomenon. And we have shown here how the saddle point is changing with time, and how they are behaving. So we can see that. Now we have changed the orientation of the two cylinders. Now we can see that how basically they will behave, the flow will behave if I take them side by side. So in literature also there exists a few study on this, but only for simple flow. But for shear flow, only one result is available. But that means we have done here a more extensive study on that. So we can have some again some new flow phenomena we have seen. So here also we have taken three different distances between the two cylinders. So first starting with S by D means the distance is half of the length of the cylinder, square cylinder, and you can see the interaction is more because there is very less. So basically basically interaction is also more, and you can have for k is equal to 0 itself, I can have a complex flow phenomena, right? So there is the interaction of the upper and lower, lower vortices, and they are basically making a two vortex setting one by one. But if I check with k is equal to 0.1, means if for the shear flow, you can see that the flow is going in the upward direction, because due to the shear nature. Because shear nature means it is the velocity will be more in the positive y direction. Okay, so for the distance is 0.5, we can have a quite interaction between them. But if I increase to 0.1, 1.0, so here you can see, though there is an interaction, but that interaction is more between the two things. Here you can see that the vortex is more that means stretched due to the effect of the distance gap. So due to the gap, this both the upstream that is downward vortex from the up cylinder and upward vortex, that means the top vortex of the downward cylinder, they are mixing up well, and due to that there is a stretch in the vortex formation. So size of the vortex is more when basically it is coming from the top, but from the interaction it is more stretched due to the distance between more distance between the two cylinder. And when we take three means there is a huge difference between these two, so there is no interaction between them. That is basically called two single vortex setting. So it is called S2. If we say S2 means, you can see two pair of cylinder is this setting from top and bottom cylinders, and interaction is no more there. But due to the effect of the what is called this shear parameter value, you can see the interaction is there. So downward cylinder almost suppressed, the vortex is not setting at all, but from the top cylinder the vortex is setting, but also due to the effect of the shear parameter, that means one is size is more, from the top size is more, and from the bottom this is suppressed and it is cylindrical shape is there. And for k is equal to 0.4 also, you can see that the vortex is setting from the top cylinder, but bottom cylinder there is no vortex setting. So this is also a new thing. Now we have taken a different aspects, which is basically, you can say that somehow these two, this is three cylinder of V shape, and these two basically you can say that control is behaving like a control cylinder for this vortex setting from this C1. So C1 basically we will be considering is the upstream cylinder, and C2 and C3 will be called as downstream cylinder. And we have taken this length is fixed 2D. We have taken this length, means the distance between C1 and C2, C3 is fixed, and we have changed the distance between C2 and C3. So if I change the position, if I this S is changed, or if I increase or decrease the value of S, then we can see that there is a huge difference in the flow phenomena. Boundary conditions are same as it is. So if I see that in the beginning, when they are very close to each other, for S by D is equal to 0.6, there is no vortex setting. So vortex setting is totally suppressed due to these two downstream cylinders. Basically they are here, they are basically behaving like a control cylinder for the cylinder for the upstream cylinder. But you can see that due to the effect of the shear parameter value, though it is there is no vortex setting, but you can see that the flow is basically that means stretched towards the upward, because due to the effect of the shear parameter value. But vortex is totally suppressed. First, when we take, there is a difference between these two downstream cylinders is 2D, means the 2 times the length of the square cylinder. Then you can see that there is an interaction, but the vortex is setting, and this vortex setting is, you can see vortex setting is basically happening, though the vortex is suppressed from the upstream cylinder, but from the downstream cylinder there is vortex setting, but from the top downstream cylinder it is happening from the bottom side, and from the bottom of downstream cylinder it is happening from the top. And with the increase of k values, we can see that the vortex heading, okay, is something okay, different, because in this case the vortex is heading from from the top downstream cylinder is from both top and bottom, but for other cylinders there is some interaction between them. So interaction is happening, but due to the distance that the flow from the upstream cylinder is interacting with the vortex setting of the downstream cylinder, and they are making a complex flow phenomena. Now, if I take r is equal to 200 and this distance is 1, you can see that the flow phenomena is more complex, because now velocity is more, and due to that the flow, downstream flow of the upstream cylinder is interacting more with the downstream cylinder, and due to that the flow is behaving, okay, totally a different, okay, way. You can see the complexity is more in this direction, and due to that, okay, your flow phenomenon is also more complex. And it can be seen from this also, but when it is 3, you can see that now a vortex is heading from the upstream cylinder also. So now we can see that the vortex is heading from the upstream cylinder, because now we have enough space to shed the vortex from the upstream cylinder. So there is basically 3 different, okay, vortex is heading from 3 different cylinder, but after a certain time, okay, in the downstream they are interacting with each other and making a couple of vortices. So there, that means these three okay, different cylinder is having different, okay, vortex heading, but after some time in the downstream they are basically interacting with each other, and interference is there, and they are basically making a that means we can say the hybrid vortices, okay, which is going to shed in downstream. So this is quite, okay, a different phenomena from the previous cases. And if I see the timetable is the first, second, third, fourth vortex, because here as the interaction is there, so we have more number of vortex is shedding. Okay, so we have here that means checked the time of occurrence and the point, okay, where it is happening, the first, second, third, and fourth bifurcations. You can see that for 0.6, okay, the distance 0.6, the fourth bifurcation is not there for k is equal to 0.1. On the other hand, if I see for s by d is equal to 2, we cannot have, we don't have the third and fourth bifurcations for k is equal to 0, and fourth bifurcation for k is equal to 0.1. So, and also if you see the time of occurrence of that, you can see that they are almost in the same time. So basically all the cases the occurrence is same, because interaction is there. So due to the interaction, okay, the k effect of the k is not so okay prominent. But if you see the distance, obviously the change is there. Okay, so these are basically some of the aspects we have seen. Now if I see for the downstream cylinder in the case of, okay, this 0.6, okay, we have not seen third and fourth bifurcations, and for k is equal to 0.3 and k is equal to 0.4, and for the fourth bifurcation for the other values. So these are some of the okay, values you can see that. But here one aspect is there, when, okay, if you see downstream, the vortex is, okay, the bifurcation is happening very early stage, very quickly after the starting of the vortex, starting of the flow. So that is a new aspect we have seen. And if I see the that means the existence of the saddle point, yes, saddle point exists, and here also we have seen the saddle point. Okay, within that we have another saddle point. So basically that means in this case we have seen also in the lower, okay, lower cylinder of the two downstream cylinder, this there has a saddle point which is, okay, which is covering another saddle point. So this is also a new thing we have seen for this case. Now after this square cylinder, we have now considered the flow per circular cylinder. So in this case, instead of taking Cartesian coordinate, we have taken polar coordinate, so that we can very easily get a body fitted grid, and we can very easily check the flow dynamics or flow dynamics. So here also we have used stream function vorticity, non-dimensional stream function vorticity formulation of Navier-Stokes equation, but in polar coordinate. So these are the equations, almost same, but here the main difference is we have 1 by r. Basically it is basically not a constant, so this is not a variable coefficient, and due to that this is more generalized form, okay, than the Cartesian coordinate system. And once you have solved this, now we can solve for any type of that means cylindrical coordinate system. Here we have shown the validation of our measure with 10⁻2000. This is experimental result, and you can see that our result is matching very well with the experimental result. So Here we have shown okay, the flow pattern and stick line, corresponding stick lines for r is equal to 100 and with different k values. So here we can see that for k is equal to 0, you can see the symmetry is there. So symmetric nature will be there because there is no okay shear. But with shear, obviously that means the downwards vorticity, okay, which is developing, is basically traced, and it is basically sinusoidal V shape, okay, cylindrical shape has that means occurred, and gradually it is going to okay the strength is going to decrease, and at k is equal to 0.2, you can see that there is only one vortex heading from the top of the cylinder. Okay, and here we have shown the lift and drag coefficients. So it is basically showing that, and the flow is periodic in nature. Okay, and that means if you see for k is equal to 0, you can see that it is coming from 0 because it is symmetric in nature, so starting from 0. But for the case of this shear flow, it is not exactly. But if you check the mean, it is quite okay, going downwards or upwards depending upon the values of k. We have shown here the phase diagram. So it is also showing that the velocity, sorry, the flow is periodic in nature. Only in this case, k is equal to 0.2, we can see that there has another small okay circulation. So that means we have a branch point here. Means we have more than one frequency. So basically, let's say one vortex heading in a different frequency, another vortex is setting in a different frequency. So this is basically showing the different frequency occurring in the downstream. For r is equal to 200, if we see the flow is quite changed. Okay, the flow pattern is quite changed. Okay, and as I told you, the symmetry is there for k is equal to 0. But obviously that means for non-symmetric okay case means k non-zero values, the frequency is okay changed and the flow pattern is a little bit changed. So we have studied other things also, but we have not discussed because due to the shortage of time. Just I want to okay give some more exposure on different aspects. So here we have seen, you can see that in this case k is equal to 0. Okay, not this is b. So not k is equal to 0.5. Basically, it is a mistake. K is equal to 0. You can see there is a symmetry from at y is equal to 0. But in this case, you cannot have a symmetry because there is more than one frequencies. So vortex is heading, but the frequency of okay this vortex heading is not same. Means there are different okay vortex heading happening okay in the downstream. Due to the, you can see that, for example, if I take this k is equal to 0.2, you can see obviously I can have almost two prominent okay vortex headings. So one is from the top or one is from the bottom, and they are basically different. But in this case, you can see we are getting a very nice okay behavior of the phase diagram. Means it is showing that there is only one frequency. In other cases, we don't have that that thing. Now for the bifurcation points, for circular cylinder there is a very nice okay or very okay unique property. So for the first bifurcation, if we see that, you can see that a pair of vortices is going here, okay, very close to the surface of the cylinder. But if you see the surface vorticity plot, you can see that there is no maximum minima. It is basically crossing the y is equal to 0 axis. Means there is a bifurcation, there is a backflow, right? Negative to positive or positive to negative. But this is not satisfying the four relations which is required to say that this is a bifurcation, structural bifurcation. So bifurcation is happening obviously, but this is not structural bifurcation. So in literature, it is basically called parabolic. Okay, this saddle point. So it is called a parabolic saddle point, not the bifurcation. Okay, so the first bifurcation is not a bifurcation. This is basically due to the smoothness or parabolic nature of the flow. And first bifurcation occurs for the second point. Okay, and if I see that, you can see that okay for particular okay time, I think t is mentioned somewhere there, 0.776. So in this case, you can see that for that there is a slight okay deviation of the fluid layer from the surface of the cylinder. There is a detachment. Before that, there is no detachment, and after that, there is a full vortex, and that can be seen from this okay thing. So you can see that particularly this point, there is no touch. It is not touched the thing. Another thing is totally crossed. Only at this particular point, it is just touched, but no other points are touched. Okay, and at the particular point, you can see it is also going downwards. So basically, it's satisfying all the four conditions, and I can have a bifurcation point here. So if I see You can see that for k is equal to 0 as discussed. So there is no primary bifurcation of the first. Okay, bifurcation is not the structural bifurcation. Also, the second bifurcation is not the structural bifurcation. For k is equal to 0.05, the first one is not a structural bifurcation, but second one is a structural bifurcation. And for k1 and k2, we have both first and second are the structural bifurcations, satisfying the 4 conditions. Okay, and in the next case, r is equal to 200, k is equal to 0. The first bifurcation is not the structural bifurcation, but second one is structural bifurcation. And the same thing for k is equal to 0.05. So this is totally different aspects or different phenomena for a flow past circular cylinder, okay, than a flow past square cylinder. So this is a this is a totally different aspects, which is okay. Which basically this vortex or this bifurcation is basically, as I told you, called the parabolic saddle point. Now, for a fully developed flow, if I consider a fully developed flow, okay, then I have taken a particular period. Period means for a full period, and we have seen that how the bifurcation is happening. So in terms of, okay, let's say I am taking that this is my t0, this is my t by 2, and this is my full t. So if I take this full time is a t, so I can divide it by, I say, 3 points. So 0, 0 plus, then this is t by 2, and this is t. Okay, or anything, I can take that it is, let's say, some t, then t plus t by 2, and then 2t. That is also possible. So basically, I have taken a particular period, and then we have seen that the bifurcation is happening at particular. Okay, this is the position. Okay, r theta, and this is the time 0t plus 0.614. So basically, if I start, this is my 0 point. Okay, and then it is basically 0.612, and this is basically shown for any any fully developed flow. So flow past circular cylinder, we can see that these are the primary first and structural bifurcation and second structural bifurcation, which is basically developing from the surface of the cylinder. So in this case, for k is equal to 0, we can see that the bifurcation, first bifurcation and second bifurcations are the structural bifurcations. Okay, but initially they are not. Now, after checking the flow phenomena, okay, or vortex heading behind the solid surface, we have now tried to check the vorticity control by using some control plates or control cylinder. So now, whatever we have seen, now we are using some control plate so that in a different position to check that how this affects the vortex heading. So here we have taken 3 different cases. One is, let's say, with a positive 45-degree angle, negative 45-degree angle, and it is equal to 0 angle. So basically, these are 3 different cases. I have put it together, but we have shown it separately. So this is basically a comparison of our result with the existing result of Ali et al. 2007, and we can see that the result is matching very well. So we can now study our things. So here we have shown the streak line patterns for k is equal to 0, for k is equal to 1, for k is equal to 2, and for k is equal to 4. And you can see that due to, and here you can see this row basically is showing that the plate is the middle point. This is state case 1. Okay, so basically this is case 1 when in the middle. Upward it is case 3, and downward is case 2. So basically here it is the case 1, it is downward, it is case 2, and this is case 3. So you can see that the vortex heading is quite different for different k values, but overall there is no such changes, right? For basically for k is equal to higher k values, the effect of this line or the effect of this control plate is not that much. But obviously, if you see in the flow phenomena, okay, very closely, so there is some effect in the near to this control plate. We have not shown here. If you see this in zoomed portion, you can see that due to this plate, control plate, the vortex heading from top and bottom, okay, is changing with the change of k values. You can see that here almost this is gone. But as I told you, this is not having that much effect. But if I take a downwards or upwards, you can see that there is a change. So here, if you see these two values or these 3, when it is middle, there is no such difference. But when I am taking a downwards or upward angle, then you can see that for this case it is almost suppressed, and for the third case, the upward vortex, then vortex from the upward top position, okay, it is basically suppressed. And accordingly, you can see that the difference, the things are happening in the same way, but due to the increase of K values, the velocity pattern or the vortex shading pattern is changed along with the size of shape of the vortices. And here we have shown that lift coefficient with time. So for the first case, when I have taken a that means plate exactly along each direction, so there is no such thing. It is basically almost same. But obviously, when I'm taking the lower one, that means downwards, so the lift is gradually decreasing, and for upward, lift is gradually increasing. And if I take the bifurcation points, so if you see that, so for case one, it has no such that means no such follow pattern, it's not following any pattern. But for case 2, when it is downward, you can see that taking extra time to get the first bifurcation, and for upward it is also going down, which is taking less time to get the first bifurcation. But for the second bifurcation, you can see that this case 2 middle, it has a stiff upward, means taking extra time to with K values. And for the second case, it is also increasing, and for our downward case, means case 3, it is gradually decreasing and then slowly increasing. So these are some of the aspects we have seen, though they are not following any particular that means direction. So obviously you can have some idea how they are behaving if I have a control plate in that. So now this is another very important study we have done. In this case, instead of taking plate, we have taken a small control cylinder here, and we have taken 3 different cases with the distance d by 2. So this is in the top, it is in the bottom, case 2, and it is both. We have taken both. So in this case, you can see that for when I have taken a that means small cylinder, control cylinder in the upward direction, so the flow is basically stretched towards the downward, and you can see that it is happening for different K values. But if I take the control cylinder in the downward, the flow is that means forced to in the upward direction. So basically, though in both the cases the vortex shading is there, it is also complex in nature, but it is periodic. But it is going in the downward direction, and for the second case too, it is going in the upward direction. Now when we put these 2 cylinders together, we have seen a totally different result. It is basically suppressed all the vortices, and for all the cases, k is equal to 0, k is equal to 0.5, and k is equal to 1. And so this is a very interesting result we have found, and this is basically the first time we have seen that if I put a control plate in this arrangement, it can suppress the full vortex shading. It was presented in a conference in Singapore, and it was then this paper got the best paper award. But the idea is now the researcher in IIT Kanpur, they also have used this idea for simple flow, and they also have found the same behavior, that they are basically suppressed. So this is one of the very important study we have done, where we can see that using these 2 control cylinders, we can totally suppress the vortex shading from the in the downstream. So these was some of the things. And if you see the lift coefficient, how they are behaving. So if you see the main cylinder, in the case of first case, so main cylinder, the lift is basically gradually increasing with increasing K values, but there is no such change in the control cylinder. On the other hand, if I take the case 2, then here the lift is almost same for the main cylinder, but it is gradually increasing with the control cylinder. But if you see here, we have a periodic nature. Here also we have a periodic nature. But in this case, as there is no vortex shading, so we have a lift is totally a single line, means it is constant. That means it is also showing that there is no vortex shading happening. So this is basically that means the confirmation of what we have shown in the vortex shading. These vortex shading contours, and after that, we have shown here. So we have now working on the this control plates for the circular cylinder problem. So nobody has studied these problems. In this case, what we have done, as we are taking a then a polar coordinate system. So we have taken the vertical cylinder, okay, a bit stretched because we want to use our body fitted grid. So my control cylinder is a bit small stretch, and this is the length is almost same of the radius of the circular cylinder. So I can show you, okay. And yes, one important aspect. So basically, this is not this is only for k is equal to 0 I have shown here, but k is equal to 1, 2. Okay, study is going on. It is under, okay. That means it is just under preparation, and we are working on that. So if you see, one important aspect what we have seen that is totally different from all the aspects that we have seen. So if I see that, you can see after some time it is almost steady. So basically, the wake length is increased but up steady. But if we compute, okay, a bit for more time, then you can see that the flow is gradually going to unsteady, going to be unsteady, and we can have a look. Now it is going to be unsteady, and we can have a vortex shading, and we can get a periodic nature or common vortex state. Now you can see that it is totally a common vortex state. So this is a new phenomenon. We have seen that due to the control plate, in the primary stage, the vortex was, okay, steady, or the flow was fully steady. But after that, the vortex start, okay, that means onset of asymmetry, and it is basically that means okay, shown a periodic nature of the flow. So, and this is basically for this is for the case of, okay, this is when I have taken a distance of 0.5. So this is a 0.5 distance, 0.5 of the radius. Now if I take a 3, means I have taken a far away. So in this case, we have seen that around t is equal to 300. Okay, t is equal to 300. This starts. So this is basically t is equal to 300. We have seen that first start the onset of asymmetry. Means here this asymmetry. Okay, you can see, and it is around 350 or 400. We can see a fully developed flow, and where we have periodic nature. But for when we have, okay, taken the distance a bit higher, means 3D. In this case, the steadiness is more. So in this case, this steady state, okay, that means is, okay, still there up to t is equal to non-dimensional t is equal to 600, almost double to that. And then we start, okay, this unsteadiness shown unsteadiness, and then automatically after that we can have this periodic nature of that. So if I show you animation, the last animation of my talk, you can see that there was a unsteadiness. Okay, so it was unsteady. After some time, you can see it is totally stopped, and it is going and going and going. I am just taking it up to this. Still it is here. Still it is unsteady. So that is around t is equal to 600. There is just little bit of, okay, unsteadiness develops, and ultimately we can see a okay, periodic nature of the flow at around t is equal to 600 or 650, and then it basically gives you exactly, okay, what we have seen without the control plane. So this control planes give a, okay, new phenomena, which basically gives 3 different regions. One is primary stage when we can have, okay, unsteadiness, though the is in the form of increasing the wake length. Wake length is increasing. After some time, wake length increased, and after some time it stopped. Means there is steady state. Okay, then there is a region when it is fully steady state. After that, we can again get unsteadiness. Means we can have the that means onset of asymmetry here, and then we can have the periodic vortex shading phenomena. So this is totally a new phenomena, or totally different phenomena. What one can see for the square cylinder, square cylinder problem. Where for the circular cylinder problem, that is a totally a different 3. Basically, I can say the three time domains, but we can have 3 different flow phenomena. But we also have seen that if I increase the distance up to more than 5, means if I take okay, the distance is 6d, then we have seen that there is no unsteadiness. Okay, after some time, after 800 also, t is equal to 800 also, we have not seen any unsteadiness in the flow. Means it is stable, and it is fully stable up to t is equal to 800. Okay, that means we can see that after certain, okay, certain that means after increasing the distance up to that means 6 times the distance, the length of the radius, we can see only a steady state. So basically, it is first few time interval. the wave length will be increased, and gradually it will be stabilized. It will be stable. Then the steady flow will occur, and it will be steady for, that means up to 800 we have tested, it is fully steady. So maybe that the due to the control plate, the flow is the vortex setting is suppressed, due to the position of the control plate. So this is some of the aspects we have discussed. We also have other studies, but we have not discussed here. But I hope all these studies give you some idea about how this complex fluid flow, basically shear flow, behaves. And if you see all the most of the highly viscous fluids, like if you see petrol, diesel, they also this the same type of phenomena. So any viscous fluid, they have this behavior, and using this idea or using this flow mechanism, flow phenomena, we can use this aspect for any different type of physical problems to control or to increase the what is called, to increase the vortex shedding. We have not discussed here. We have another problem we have studied. In that case, we have seen that, like just for example, I'm just giving one particular problem. Here we have taken the control plate here, right? But if we take the control plate in the upward, then it will increase the vortex shedding. Totally different phenomena. We also have tested that. So that means if we want to suppress the vortex, so this is, if we put the plate in the downstream, it will suppress. But if we put this in the upstream, then we have seen that the vortex shedding is more than usual vortex shedding. So if we want to increase the vortex shedding, we can use the control plate in accordingly, and if we want to suppress, we can also use this accordingly. So basically, that means many times we need to increase the vortex shedding, to get more vortices. Sometimes we need less vortices to stable the things. Means when, let's say, for digging the crude oil, we need minimum vortices, so that there should not be any incident happening. On the other hand, let's say, for example, washing machine, we need, or let's mixer, so we need more vortex, more turbulence. So in that case, all these things may be useful, or it can be used in a different way in real life, applications. So overall, the conclusion is that we have first studied this square cylinder problems, and then we have studied the interference between 2-cylinder, then 3-cylinder in V-shape. Then we have extended our work to circular cylinder, and then we have studied different control plate aspects, for the square cylinder and for the circular cylinder. And we have seen very nice properties and very nice phenomena which has not been studied beforehand, and many new things which is still that means to be studied, which is we have got it, but we have not studied yet. So that is also there. So we will study in near future. These are some of the references, and thank you for your kind attention. I hope I am in time.